Milky Way, there are lots of stars, and each of the stars have the motion, but also the chemical composition. And the motion and the chemical composition will contain the history of the galaxy. You can think about, like, if you look at Columbus, the people in the city will tell the story of the city. So that's the same thing for galactic archaeology. So we are using the star as the tracer to unwind the history of the Milky Way.
From the heart of The Ohio State University on the Oval, this is Voices of Excellence from the College of Arts and Sciences, with your host, David Staley. Voices focuses on the innovative work of arts and sciences faculty and staff, with departments as wide-ranging as art, astronomy, chemistry and biochemistry, physics, emergent materials, and mathematics and languages, among many others. The college always has something exciting happening. Join us to find out what's new now.
Joining me today in the ASC Marketing and Communications Studio is Yuan-Sen Ting, Associate Professor of Astronomy and a faculty member at the Center for Cosmology and AstroParticle Physics at The Ohio State University College of the Arts and Sciences. He is also an adjunct scientist at the Max Planck Institute for Astronomy. His research is at the intersection of artificial intelligence and astronomical research, combining computational methods with astronomical data to study galactic archaeology and stellar evolution. Dr. Ting, welcome to Voices.
It's a pleasure to be here.
And I'm very interested in your use of large language models, which of course are very, very much in the news today. And we're having all these debates at the university about, should students be using large language models? You're using large language models to study astronomy. Tell us about this research.
Yeah, so a big part of my research is what we call the agentic research. So we try to use the language models as a helper and try to automate the research as much as possible.
Well, let's first of all start with agentic research. Yeah. What does that mean? What is an agent?
Yeah, so the agent here will be the chatbot. So the chatbot is serving as an agent. And we call that agentic research is just because quite a lot of the chatbot are still not human-like, so they have many shortcomings. So we need to help them to do the task. So to build around the ecosystem, so that we can mitigate some of the shortcomings and to make them more like a researcher. And hopefully we can get to the stage where most of the research can be automated.
Well, there's a lot there I want to unpack. So you described the chatbot as a helper.
Yeah.
In what way?
So for example, so the chatbot have some reasoning ability, but it's not as strong as humans. So we know that the chatbot is pretty good at writing code and finding information, and maybe to some extent to come up with new ideas. So we try to have that. So we call that self-driven lab, but it just means that, as the name suggests, we hope to have the lab that is more self-driven. Of course, the current AI is still a bit far from the holistic ability of human. So we are trying to make sure that the agent, the chatbot serving as an agent, will expedite some of the research.
What do you ask the chatbot to do? What role is the large language model playing in your lab? Yeah,
so for example, we recently finished a research work on James Webb. So
the telescope, the James Webb telescope.
Yeah, so James Webb, of course, are collecting a lot of data. And most of the sources are pretty boring because we know the Milky Way is pretty normal. But the goal here is to find some interesting outlying sources. And what we define as outlier is really hard to code up in the classical computer science way because there's no one algorithm that will say this is an outlier or not. So we're using the chatbot to think about the sources, to pull out some tools. So for example, we have some spectra from the galaxy, and then we say, try your best to explain the spectra. So the chatbot will go to write code and try to change some of the physical assumption that we deem to be reasonable. But despite their best try, if this is something that we still cannot explain, then this warrant more investigation. So then the human can jump in. So now the human do not need to go through all the sources because it's triaged by the AI.
Well, that answered, I guess, my next question, which is why can't human beings do this sort of work, or a graduate student or an undergraduate?
Yeah, just it's a scalability issue. So there are two things, right? One is that the task is pretty boring.
Oh.
So if you try to reason about one galaxy, it's fun. but we are routinely looking at millions or billions of galaxies. And the way that we have been triaging the sources are pretty crude. So we might accidentally lose some of the sources, but we cannot ask the grad student to go through the millions and billions of sources. So this is a regime where the AI can help.
You had also said earlier that you are helping the AI, helping the large language model do a task. What role are you playing in helping the large language model?
Right. So there are a few things here. So most of the time, if you think about a chatbot, if you just ask a question in ChatGPT, the chatbot might, what we call, hallucinate. So we will try to make up some results. And we know that we can help the AI if we give the tools to the AI. For example, in astronomy, we have some standard code that we use to analyze the galaxy spectra. So instead of just asking the AI to start from scratch, we are saying that these are the 50 tools that you could use, and you can decide when you want to use tools. So you're laying out all the possible tools and teach them to use the tool. Mm-hmm. Yeah. So AI is kind of like a grad student in a way. So you lay out all the tools and you try to make them more smarter over time. And the other part is that the AI can also self-improve, right? So if you have 50 tools and they try a certain tool for a certain task, but it does not work, then you can reinforce the successful behavior and try to avoid them to use the wrong behavior.
Are you using sort of an off-the-shelf large language model or something maybe that you've coded yourself?
Yeah, so it's a range of things. So in my research group, we use both the proprietary models and the open source models. So the good thing about the proprietary models is easy to use. So most of the companies make them as easy as possible, and they are usually also quite robust. But the downside here is that using the proprietary models, we cannot do a lot of training. So even though, say, GPT-5, you can do what we call fine-tuning. You can fine-tune the model a little bit. But because they are not open source, so you cannot do a lot with them. So the open source model, a few years back, of course, are lagging behind the proprietary models. They are now also catching up quite quickly. The advantage of having an open source models here is that now you can basically improve them more than you could with the proprietary models, because you have all what we call the neurons weights. So you have the whole neural network and you can train in whatever way you want. So it's actually both. So we use the proprietary models as a baseline, and then we are also training the open source models. Quite often it's really a cost and a benefit trade-off. So we are hoping that using the proprietary models as a benchmark and say, can we do that with a smaller, cheaper, and more eco-friendly models?
Mm-hmm. You referred earlier to the reasoning capabilities of these tools. Say a little more about this. Are they in fact reasoning in the way that you and I might reason?
Yeah, that is a really big topic. I don't think anyone know the answer. So it definitely has some aspect of reasoning, right? So if you think about most of these models, they are already achieving gold medals, like a capability for the high school Olympiad, right? So in fact, like at OSU here, we are finishing a project that we are testing them on the astronomy Olympiad this year. And they are also achieving gold medal standard, meaning that comparing to the brightest high schooler that we have, they are achieving gold medal capability of math and coding and physics. So they are definitely doing some form of reasoning. But of course, the reasoning is a very big terms, right? So the obvious limitation is what we call the Moravec paradox. So meaning that something that we think are very trivial. So for example, the AI are still really bad at doing what we call the common sense of physics, like knowing that the water should flow from the top to the bottom. So this turned out to be extremely hard to train, and there's also good reason to understand why that happens. So you can think about AI training is inversing the evolution. So things that appear last will be the easiest to train. So if you think about the human brain, the frontal lobes are developed pretty late. So this is why lots of the thing that we prize for, like math and physics, this turned out to be quite easy to imitate. But the things that are more primal is quite difficult. So the difficulty of using AI as an autonomous agent is that it has some of the ability, but it still lacks so much of the primal ability that we have.
I've also heard it said that it's because they lack experiences. For instance, we all understand water goes from top to bottom because of our experiences. AI lacks those kinds of experiences, and therefore it's harder for them to figure that out. Is that a fair assessment? Or
I don't think it's more just the experiment, because we simply do not know why the human are so good at a certain thing. For this type of research, we usually construct benchmark. So benchmark is kind of an exam for the AI. And there is a big field of research to find things that are very easy for human. Basically, even a youngster or kids can do correctly, but AI fail. And there are still a lot of such tests. Simply because I think the evolution take a long time to get to the stage that we are. And it's really hard, and the brain is very efficient machine. So most of the AI that we have are not that efficient. So to answer your question, I think the reasoning is so depends on what you meant by reasoning. So if you're doing some mathematical derivation, even though it's not at the genius level, I think it is getting really good. But if you ask some of the simplest question, like the games that the kids would play on the phone, the AI might not be able to do that.
Are these agents able to generate hypotheses?
That is another big range of big topic that people are exploring. So the question there is that it's not that they cannot come out with good ideas, but just how we validate that. So for example, in astronomy, it's always not hard for AI to come up with some idea. We would not know that it's a good idea or bad. So for example, the AI can make up a new model for dark matter and dark energy. I don't think the challenge is to come out with idea. The challenge quite often is come down to how do you go from that idea and run the simulation and collect the data and do the analysis. So the whole pipeline is difficult. And this is what we meant by self-driven lab. So self-driven lab is not only just to come out with good ideas, because the good idea is the one part of it, but how to build the whole pipeline so that when the idea is proposed by AI, the AI can also execute those ideas.
Can you imagine a day where that happens, or that sort of that pipeline is completed?
I am both optimistic and pessimistic. I think if you ask the people that do research in the area, I think we span the whole spectrum. There are people that are highly optimistic. There are people that are highly pessimistic. Myself is actually somewhat in between. So I feel some of the science can be done by AI. But because the AI are still lacking so much of the ability that we have, so the question becomes not AI is not substituting the researcher. It's just what type of the research can be done by AI while still being impactful. And I think this is the question that my group try to explore. So if you think about a Venn diagram, that is a set of the question that the AI can do. There's also another set of questions that we deem to be interesting. The overlapping area is still pretty small, partly because the ability of AI are still lacking in so many areas. So for AI to be completely human-like, personally, I am more pessimistic on that end, but I also feel the ability of AI is keep gaining. So as it gains, the intersection in the Venn diagram will become larger and larger over time. So key here is to identify an interesting question that the AI can handle. Then you can make some breakthrough.
Are the AIs capable of generating those questions? Or is that's the role that humans play?
So that is very field dependent. So astronomy, we don't have such problems, because part of that is that we are pretty useless. So whatever we do as a research has no impact to the human life. So when we do astronomy, you have so many questions to ask, and most of the questions are valid by themselves. So it's not understanding a planet outside the solar system is more noble than understanding a galaxy outside the solar system. So the advantage of being astronomy is that all questions are equally interesting. There are no, this is more noble than the other. But the question is, okay, with the current technology and also with the current capability, like the James Webb that we just mentioned, or the Roman that will be launched soon. So what, with the current data, what are the new frontier? So we are always looking at the new frontier instead of saying that these are the questions and build tools to solve that. Yeah.
So you're obviously at the forefront of this sort of research. Do you think that using AIs, using agents, will just simply become a standard part of how you do astronomy? It's how one does astronomy. One does it with the assistance of an agent.
I think it should be. There's no reason to not get help for things that the AI are very good. So it becomes things that we have been using all along, like the calculator, or like we use coding. So it becomes part of the routine. But also like depending on because the astronomy is a very big field, I can also imagine that there are still subfields in astronomy that will still be untouchable by AI, because most of the thing that is needed there is hard to be achieved by AI. So for example, if you do instrumentation science, then I think even though AI might propose some new material to build the instrument and all this require quite a lot of human effort to do that. But if you're doing something more along the math and statistic part of astronomy, then the AI can expedite a lot more. That's just because a big part of what we do in mathematical physics or astronomy, for example, like if you want to do some long derivation, it would be silly to write down line by line. So even though the sketch of the proof can be done by you, but the intermediate step can be filled in by AI.
Are you instructing your students, your undergraduates, let's say, are you instructing them not just to use AI, but how to use AI?
Yeah. So I have the pleasure to teach the Python 101 for scientists. So we call the astronomical data analysis. So it's a 1,000 level courses. So it's for the year one students. So they are learning coding from scratch. And we are at week 4 now. Actually, this week I am teaching how they can use coding to interact with AI. So you can use coding to interact with AI. And so as I mentioned, like building tools for AI to use. So not only just go on to ChatGPT and just have the interface, but you have a different interface where you can build small tools for the AI to use. Myself, I encourage students to use AI for coding. That, of course, that create a lot of challenges on how you teach coding. So in the past, when I learned coding, and I'm not even that old, right? The coding course is so boring because I have to learn the syntax. It's just English. But coding nowadays, the AI can write the code for you. The important thing is for you to understand if the code is correct or not. So I switched the courses now to say all students should write code with AI, but I will test you on the understanding of the codes. In fact, I use the AI to test them. So I make AI to write the wrong codes. So the student has to identify what is wrong with the code. Yeah, so it's a different type of teaching. And of course, there are things that I am worried myself because my colleague will ask, is this the right way to learn coding? So maybe the muscle, the memory that how we learn is one way to internalize the knowledge. That could be true, but I think we are at the cusp of transition that no matter what you say, the student will use AI by default. The question is, how do you make it a useful way to teach? And exactly because AI are still lacking of so many things, students should learn how to be skeptical about the output of AI. So I make the jokes in the public talk the Sunday before last week that students are usually quite skeptical about the human professor, and that should apply the same skepticism to it. So now my teaching is more about making students to be skeptical and critically think about the output of the AI.
So earlier you maybe compared a large language model to a graduate student.
Yeah.
Would it be an exaggeration to say that the large language models, the agents, are a member of your lab, like a postdoc or a graduate student, or you as PI?
It could be, but it's not a perfect analogy because it's really more like a computer because it's really good at something. It's very strange to say your calculator is part of your lab. So when you say about something is a member of the lab, quite often you mean the holistic ability of the human, right? So you interact with people, you come up with good ideas, you move around the lab. And AI is really good at something, and sometimes is superhuman, but they are really good at a certain area. But it's just a bit strange to call them a member. So it's a useful tool. Yeah.
Where did your interest in AI come from?
Yeah, so my background is more on the mathematics. So my undergrad is more on the mathematical physics. So I'm always interested in mathematics. And I'm always interested in the analyzing big data. And my interest in astronomy comes from the fact that I would love to design like algorithms that have no impact to human life. Because I always find that a bit scary if I work for YouTube or or Facebook or Google. Is they are doing a lot of good, but you're also making the decision for people, right? So I come from more a statistical background, so I would love to understand how the math and statistics works, but also I want to stay away from affecting the human life as much as possible. And exactly because I come from the statistical background, I started my grad school in 2012, and then I joined the Lindau meeting. So there is a meeting in Germany. And I remember that time, the 2013 is the starting booming of deep learning. And then a speaker just say, there's this new thing that appeared to be quite promising. Like new thing is a bit odd because the neural network is pretty old, but they say this is something that you should pay attention. And that caught my attention just because coming from a statistical background, that seems like a very natural extension. So a lot of my earlier work, like before ChatGPT, like before I go more onto the agentic stuff, is mostly using AI as an extension of the statistics.
Mm-hmm. Became new again. Neural networks became new again.
Yeah, but it's a very old technique.
Yeah.
It's grounded on quite a lot of things. Yeah.
Yeah. So why astronomy then? Why, if you're so interested in math and statistics, why astronomy?
I think partly because astronomy is really a perfect sandboxes. Because we have the open sky policy, so most of the data are public. So we are not, the stonewall by. If you do work on in chemistry or medical science, like the data are quite hard to get. And exactly because we always make jokes that our data have no value at all, but it's become like a perfect way to experiment things. So to say no value is an overstatement, but I think this is exactly the beauty of astronomy. So you can say that the astronomy has no impact on the human life, but a lot of the algorithm is developed in astronomy and physics exactly because we have the open sky policy, and people like myself who are interested in building models, understand AI and math, is a great sandbox to experience. Yeah.
In my introduction, I said that you were interested in galactic archaeology. So I know what galactic means, and I know what archaeology is. What is galactic archaeology?
Yeah. So it's not archaeology. We were just joking that my best friend in grad school is archaeologist, earthbound archaeologist, but we are the galactic archaeology. So the name comes from. So what we call galactic archaeology, so the galactic, so we start with a big G. So it's just a funny thing in astronomy. So the other galaxy is with small g. So when we say a big G galaxy, it's the Milky Way. The galactic part here is referring to the Milky Way. And we call it archaeology because we are using the star to trace the history of the Milky Way. So, like in the Milky Way, there are lots of stars, and each of the stars have the motion, but also the chemical composition. And the motion and the chemical composition will contain the history of the galaxy. You can think about, if you look at Columbus, the people in the city will tell the story of the city. So that's the same thing for galactic archaeology. So we are using the star as the tracer to unwind the history of the Milky Way, and hence the archaeology.
And AI agents have assisted you in this work?
Yeah, so lots of the galactic archaeology, because is particularly in Milky Way stuff, there are lots of, so given an observation, exactly because we are working in astronomy, you cannot repeat the experiment. So quite often you are really dealing with a crime scene. You have a crime scene and you try to figure out what is wrong, what happened to the crime scene. Of course, your human brain can only come up with so many ideas and hypotheses. So this is a part where the agents can jump in and say, hey, given the observation, you might also want to consider this direction and that. So in that way, it has been very, very helpful, not only in galactic archaeology, but in astronomy in general.
Tell us what's next for your research.
Yeah, I think my research now is starting to move toward more on the large language models. So in the past, I do maybe half on advancing the statistic with AI, but the other is using the large language models. But I'm really quite curious to figure out what is the limitation of using large language models as an agent. So I don't think, exactly because it's really quite an early stage, I really want to make it clear that, like despite a lot of the optimistic hypes and promises, there are so much challenges. The idea of automating part of the research with AI is such a rich field. So I think I'm moving more in that direction, just figuring out what is the limitation, and is there any interesting question that we can solve with that.
Yuan-Sen Ting, thank you.
Thank you.
Voices of Excellence is produced and recorded at the Ohio State University College of Arts and Sciences Marketing and Communications Studio. More information about the podcast and our guests can be found at go.osu.edu/voices. Voices of Excellence is produced by Doug Dangler. I'm Jen Farmer.